Alaikum girls, I am Shamsunisa from Royal Degree College Chemistry Department. As we are seeing about Unit 3rd Physical Chemistry in that Chemical Kinetics, today we'll study about effect of temperature on rate of reactions, concept of energy of activation, calculation of activation energy, ARHENIUS equation, calculation of EA from graph, problems, simple collision theory of chemical reactions, steric factor, and absolute reaction rate theory or transition state theory. So first of all, we'll see about effect of temperature on rate of reactions. Generally, the rate or velocity of a chemical reaction increases with rise in temperature. For every 10 degrees centigrade rise in temperature, the rate increases by twice or thrice. This increases in the reaction rate with temperature is expressed in the form of temperature coefficient. Now we'll see what is temperature coefficient. It is nothing but it is the ratio of rate constants of a reaction at two different temperatures differ by 10 degrees centigrade. The two temperatures are generally taken as 35 degrees centigrade and 25 degrees centigrade. Therefore, temperature coefficient equal to Kt plus 10 degrees centigrade divided by Kt or K 35 degree by K 25 degree, which is approximately equal to 2 or 3. So what is K 35 degree? That is equal to rate constant at 35 degrees centigrade, and K 25 degree is rate constant at 25 degree centigrade. We'll see the example. First example, the temperature coefficient for the dissociation of hydrogen iodide is 1.7. Here you can see the reaction, 2 moles of hydrogen iodide dissociate and we will get hydrogen and iodine. Here the temperature coefficient value for this dissociation is 1.7. Then second example, we'll see the temperature coefficient for the reaction of methyl iodide and sodium ethoxide is 2.9. You can see the reaction here, methyl iodide reacting with sodium ethoxide, and we are getting here the product methyl ethyl ether along with that sodium iodide. So temperature coefficient is an approximate method for expressing the effect of temperature on the reaction rate. Generally, with rise in temperature, number of activated molecules, the activated collisions increases. Therefore, the rate of the reaction also increases. Now we'll study about concept of energy of activation. For a chemical reaction to occur, the reacting molecules must collide with each other. All the collisions may not lead to the formation of products. The formation of products from the reacting molecules involve breaking of some bonds and making of others, and for this process requires energy. So the colliding molecules which possess energy equal to or greater than the minimum energy required for molecular rearrangement for products, these molecules are called activated molecules. So the collision between these molecules are called effective collisions that results in the formation of products. Now we will see about threshold energy denoted by ET. It is the energy required by reacting molecules to form products. Now we'll see about activation energy, EA. The energy difference between threshold energy and the average energy of the reacting molecules is called activation energy. With this equation we can represent EA, it is equal to ET minus ER. What is EA? EA is the activation energy. It is equal to ET, that is threshold energy, minus average energy of the reacting molecules, that is ER. So the excess energy required by reacting molecules to cross the energy barrier and form products is called activation energy. So the energy barrier determines the magnitude of threshold energy. does. According to activation energy concept, non-active molecules can be activated by absorption of extra energy. That extra energy is called activation energy. Now you can see here Et minus Er, it is equal to Ea, that is for the forward reaction. Et minus Ep, it is equal to E dash A, it is reverse reaction. So E dash A, that is the reverse reaction, minus Ea, that is the forward reaction. It is equal to delta H, which is nothing but enthalpy. Here you can see the graph. On the x-axis we are taking reaction coordinate. On the y-axis we are taking potential energy. So here average energy of the reactant, it is increasing. It is going up to the threshold energy of activated molecule, up to this level. So here activation energy is required, isn't it? Then from that the reverse reaction will take place. That is activation energy, that is E dash A, reverse reaction. And we are getting here at last energy, that is the average energy of the product represented by EP. Okay. So this graph indicates what? Exothermic reaction. That is nothing but delta H equal to negative. Different reactions have different amounts of activation energy. A reaction which has higher activation energy is slow at ordinary temperature, while that with lower activation energy proceeds faster at given temperature. Now we'll see about the calculation of activation energy at ARHENIUS equation. ARHENIUS derived an equation to study the effect of temperature on rate of reaction. This relates the rate constant K with temperature T and is used to calculate activation energy of a reaction. So the ARHENIUS equation is K equal to AE to the power minus EA by RT, where A is constant known as frequency factor, EA is the activation energy of the reaction, R is gas constant, T is absolute temperature, K is rate constant, and small e, it is also constant, its value is 2.718. Now as we are using the ARHENIUS equation, that is K equal to AE to the power minus EA by RT, applying log on both sides. So we can write like this: log K, it is equal to log AE to the power minus EA by RT. Now in the next step, log K it is equal to log A plus log E to the power minus EA by RT. Why? Because here we are applying this formula, that is log AB, it is equal to log A plus log B. See here, in the previous equation, log A into E to the power minus EA by RT, isn't it? That is log A into log B. That is log AB, we can say. Log AB, that is equal to log A plus log B. So we are writing this. Log K, it is equal to log A plus log E to the power minus EA by RT. Now, this log we are converting in the natural log, that is ln. So we are applying this value of log 2.303. Rest of the things are as it is. Next is ln and e gets cancelled. So you will get log K equal to log A minus EA by 2.303 RT. At two temperatures, T1 and T2, the above equation can be written as log K1, it is equal to log A minus EA by 2.303 RT1, it is our equation number 1. Next is log K2, it is equal to log A minus EA by 2.303 RT2, it is our equation number 2. Now, K1 and K2 are constants at T1 and T2 temperatures. Subtracting equation 1 from equation 2. So we can write like this: log K2 minus log K1, it is equal to log A minus log A, then minus EA by 2.303 RT2, then minus into minus plus, then EA by 2.303 RT1. Now log plus log a minus log a gets cancelled. So you will get log K2 by K1. Here in this we are applying formula, that is log a minus log b, it is equal to log a by b. So we are writing like this, log K2 by K1. It is equal to, see here, in the previous equation, what are the common things? EA by EA is common, 2.303 is common, and R is common. So we are taking EA by 2.303 R as common. Then 1 by this one, the plus 1 by T1 minus 1 by T2. So we are writing here like this, 1 by T1 minus 1 by T2. Thus, activation energy of a reaction can be determined from the above equation by knowing the values of K1 and K2 at T1 and T2 temperatures. Evaluation of EA from graph. See the graph here. The value of EA can be evaluated by plotting a graph between log K and 1 by T. We get a straight line with slope equal to EA by 2.303 R or EA by 4.576. From this EA, that is the activation energy, can be determined. Now we'll see the problems. We'll see first problem. The activation energy of a reaction is 168 kilojoules per mole. If velocity constant at 230 degrees centigrade is 0.163 meter mole inverse second inverse. Find out the frequency factor and rate constant at 280 degrees centigrade. So here the given data is K1 value is how much? 0.163. Okay, and the T2 value, the T1 value, that is the first temperature, how much? 230 degrees centigrade. We are converting degree centigrade to Kelvin, so we are adding 273. So we'll get 507 Kelvin. Then another temperature, that is the T2, how much? 280 degrees centigrade converted to Kelvin. So 280 plus 273, we'll get 553 Kelvin. Now we are using this one EA, it is equal to how much the activation energy value? 168 kilojoules per mole. This kilojoules per mole can be converted to joules per mole. So whatever the value will be there for the kilojoule per mole, it should be multiplied with 1000. So we can convert it to the joules per mole. So we are writing here 168 into 1000 joules per mole. And R is the universal gas constant. Its value will be constant, that you have to remember, 8.314. Now we are applying this formula, log K2 by K1, it is equal to EA by 2.303 R, 1 by T1 minus 1 by T2. So now log K2 is divided by K1. Value of K1 we know, that is 0.163. We are substituting that value. It will be equal to EA value is how much? 168 into 1000 divided by 2.303 as it is into R value is 8.314. Then 1 by T1 is 503 and T2 is how much? 553. Now in the next step, what we are doing here, listen this point very carefully. 553 into 1, 553. 503 into 1, 503 minus, then we are multiplying both the bases, 503 into 553. Rest of the things are as it is. Then in the next step, as we are subtracting here, this value, 553 minus 503, so you will get 50 difference. Rest of the things are as it is. Okay. Now we are multiplying 168 into 1000 into 50, so you will get this value. And the denominator values also we are multiplying, so we will get this value. Now we are dividing, so we will get 1.6. So in the next step, log K2 by 0.163, it is equal to 1.6. Now this log we are bringing to the other side, so it will be in the antilog form. So the K2 by 0.163, it is equal to antilog 6. Antilog of 6, antilog 1.6 we can say, isn't it? 1.6, not 6. Antilog 1.6 value is 39.8. Now this one we are going to find out the K2. So we are keeping the K2 on that side only, and this one 0.163, it should be multiplied with 39.8. Okay, so you will get the value as 6.48. That is the value of K2. Now the frequency factor at 280 degrees centigrade, we are calculating for that. Okay, so here we are applying this formula. Log K is equal to log A minus EA by 2.303 RT. Log K, the value of K is how much just now we got, that is 6.48. It is equal to log A minus EA value 168,000 divided by this one 2.303 into R value is 8.314 into T, another the T value. Which T value this one is? T2 value, that is 553 we are writing. Now we are multiplying this above numerator value, so we will get this value, and we are multiplying the denominator value, so we will get this value. Now we are dividing this both, so we will get minus 15.86. Now here what we are doing, log 6.48, log value of 6.48 is 0.811. It is equal to log A minus 15.86. Now what we are doing, this minus 15.86 we are bringing to the other side, so we are writing in the positive value. It is to be added up with that 0.811 value. It is equal to log A. Then when we are adding this both, we will get 16.67. It is equal to log A. Then log we are bringing to the other side, so anti-log 16.67, it is equal to A. Anti-log of 16.67, its value is 4.7 in 10 to the power 16. That is equal to A. Next problem we'll see, that is the rate constant of a certain reaction was found to be doubled on raising the temperature from 25 degrees centigrade to 35 degrees centigrade. Calculate the activation energy. Here is asking to calculate what? Activation energy. Given data is K2 by K1, it is equal to 2. Okay, K2 by K1, it is equal to 2. And T1 temperature how much? 25 degrees centigrade. We are adding 273 to convert it into Kelvin, so we are getting 298 Kelvin. Like that the same for the other temperature T2, 35 degrees centigrade. It is to be converted to Kelvin. We are adding 273 in that, and we will get 308 Kelvin. R value is how much? That you should remember, 8.314. Now we are applying this formula. Log K2 by K1, it is equal to A by 2.303 R into 1 by T1 minus 1 by T2. Now we are substituting the values. That is R value we are writing here. Log K2 by K1. K2 by K1 value is 2. That one we are writing. It is equal to A by 2.303 into R value we are substituting. Then 1 by T1. The value of T1 is 298 minus T2 value is 308. Now again 308 into 1, 308, then minus 298 into 1, 298 divided by the denominator should be multiplied. So now we are subtracting the numerator value. So we will get the difference as 10 divided by the same. And in the next step, what we are doing in the next step, that is the log 2. The value of log 2 is 0.3010 that we are keeping. Then rest of the things are as it is. We don't know the value of EA, isn't it? Activation energy. So we are bringing EA to the other side. Then what will happen here? If we are bringing to the other side, this whole value, that is 0.3010, this denominator, all these are cross multiplied and it is going to the numerator, and this 10 it is coming in the denominator. Okay. Then we are multiplying that numerator value, so we will get this value divided by 10. If we are dividing that, we will get the value of this particular thing. So here you can see EA value, it is equal to that this value divided by 10. So we will get the value in joules, or if it is to be converted to the kilojoules, bring this point towards this side, that is 52.89. So here we are dividing this joules value by 1000, so we will get this value in kilojoules. That is activation energy. Next we will see about the simple collision theory of chemical reactions. It was developed by ARHENIUS and Bantoff. According to this theory, the reactant molecules must collide with each other before they react. So the number of collisions per second per unit volume of the reaction mixture is known as collision frequency, indicated with Z. Now you can see this equation ZAA. Here the reactants are same. It is equal to 2 pi square d square into 8 pi kt by mu to the power half. Next, if we are taking the reactants, different reactants, so ZAB, it is equal to Na into Nb, d average to the power 2 into 8 pi kt by mu to the power half. It is our equation number 1. Now the collision between unlike molecules takes place. So mu, it is equal to reduced mass. Mu is nothing but reduced mass. Its value is equal to Ma into Mb divided by Ma plus Mb. That is the mass of reactant A and mass of reactant B. It is multiplied divided by mass of reactant A plus mass of reactant B. If we will divide these two, we will get the value of mu, that is nothing but reduced mass. That one we are keeping in our first equation, substituting the value of mu in equation 1. So we have already substituted here, you can see. Then in the next step, what will happen? It is getting reversed. That is this Ma plus Mb, it is going to the numerator. Rest of the things are as it is. ZAB is what? Collision frequency of reactants A and B. Na and Nb are the number of moles of A is Na and number of moles of B is Nb. Ma is mass of A and Mb is the mass of B. DAV, what is that? Average collision diameter. It is equal to dA plus dB divided by 2. According to hard sphere collision theory, the collision number multiplied by ARHENIUS factor, that is e to the power minus Ea by RT, gives the rate of formation of the product of reaction in terms of number of molecules formed per unit volume and per unit time. Now we are using this formula, that is rate of the reaction, it is equal to Na into Nb into d average square into 8 pi kt by mu to the power half into e to the power minus Ea by RT. Dividing the above equation by Na into Nb, okay, and multiplying by Avogadro number n. Here you can see we are multiplying this whole equation with Avogadro number n and dividing the whole equation by Na into Nb. It will give the rate constant in molar units, that is m square mole to the power minus 1 second to the power minus 1. So here what will happen? Na into Nb gets cancelled. Rest of the things are as it is. Then in the next step, that is Z, since we know that ZAB, it is equal to n d average whole square into 8 pi kt by mu to the power half, isn't it? So K, that is nothing but rate. It is equal to what we are writing here. In place of whole this value, we are writing ZAB, okay, because this whole value it is equal to ZAB into e to the power minus Ea by RT as it is. Next, we'll see about steric factor. What is steric factor? Collisions must occur for a chemical reaction to proceed, but they do not guarantee that a reaction will occur. If colliding molecules have improper orientation, they do not react even though they may possess sufficient energy. To account for effective collisions, another factor P called steric factor is introduced. So the fraction of collisions having proper orientation for conversion of reactants to products is called steric factor and it is indicated with P. Now the rate of the reaction we can write like this by using the steric factor P. Rate K is equal to P into ZAB into e to the power minus Ea by RT. Now we'll see about absolute reaction rate theory or transition state theory. Transition state theory was developed by Eyring, Polanyi and Evans. According to this theory, bimolecular reaction between two molecules takes place through the formation of the activated complex. Here you can see the reaction. A plus B, both are the reactants reacting with one another, and as a result of that, on reversible equation, we are getting AB to the power star. That is nothing but transition state activated complex we are getting. From the transition state activated complex, we are getting the product at last. So here the activation energy EA is the additional energy that must be absorbed by the reactants in their ground state to allow them to reach the transition state. If they do so, they possess sufficient energy to reach the transition state, the reaction can proceed. The rate of reaction depends on the product of the concentration of the transition state and the frequency with which it decomposes into the product. So the formula like this we can write: rate of reaction, it is equal to frequency of crossing energy barrier into concentration of activated complex at the top of the energy barrier into probability of crossing the barrier. So rate of the reaction, it is equal to 1 by delta into kT by 2 pi mH to the power half into C star. C star is what? Concentration of activated complex at the top of the energy barrier. Listen, into probability of crossing the barrier is 2 pi m kT by h to the power half delta. So here 2 pi m gets cancelled. Delta gets cancelled. Now here bases are equal, power should be added with multiplication. See, the bases are equal. kT by h, it remains. Here also kT by h. And at that time the powers can be added. Half plus half, that is equal to what? 1. So the rate of the reaction, it will be equal to C star into kT by h. So the kT by h, it is equal to a frequency. Its value depends only on temperature. Rate of formation of activated complex, it is equal to rate of decomposition of activated complex. So rate of formation of activated complex is Ks Ca Cb. It is equal to rate of decomposition of activated complex, that is C star into kT by h. What is Ks? Ks is the specific reaction rate. Ca is the concentration of A, Cb is the concentration of B. C star is the concentration of activated complex. Now, Ks we are keeping that side only. Ca into Cb we are bringing to the other side. So we can write like this: Ks equal to C star divided by Ca into Cb into kT by h. It is our equation number 1. On applying law of mass action to the following equilibrium. Our equilibrium is like this: A plus B. On reversible equation, we are getting the activated complex, that is in the square bracket we are writing AB to the power star. Okay. So K star, it is equal to C star by Ca into Cb. What is K star? K star is the equilibrium constant. On substituting the value of C star by Ca into Cb in equation 1. See, in equation 1, in place of C star by Ca into Cb, we are writing its value as K star. And kT by h is as it is. It is our equation number 2. From statistical mechanics, the value of equilibrium constant can be written in terms of partition function as K star equal to Q star by Qa into Qb into e to the power minus delta Ea by RT. It is our equation number 3, where Q star is partition function of the activated complex. Q star is the partition function of the activated complex. Qa is partition function of reactant A and Qb is the partition function of reactant B. Delta Ea is what? Heat of activation. So on substituting the value of K star in equation 2, see, Now in the equation 2, in place of K star, we are substituting the value of K star like this. So we are getting what? Equation number 4. Now the equation of the theory of absolute reaction rate can be expressed in terms of thermodynamical functions instead of partition functions. So we can write the equation like this. Ks it is equal to Kt by h into e to the power minus delta h star by Rt into e to the power minus delta s star by Rt. This equation is known as ARHENIUS equation. Here delta S star equal to entropy of activation and delta H star it is equal to enthalpy of activation. This equation can be applied to determine the rate constants of unimolecular reaction. Thank you for listening my lecture.